Welcome back to AllAboutRx. Today, we are breaking down the absolute essentials of pharmaceutics, focusing strictly on ionization, pH, and buffer systems. If you're a pharmacy student or honestly just curious about how medications actually work, this explainer is your high-yield guide to understanding exactly how drugs behave in the body. So, let's get right into it.
It's a massive question in medicine, right? Why do some drugs just effortlessly absorb into your bloodstream while others completely fail and literally never reach their target? Well, the answer lies in the chemistry. Okay, let's dive into this.
Here's a quick look at our roadmap for today. 1. Ionization and drug absorption. 2. pH, pKa, and equations. 3. Buffer systems and capacity. And 4. Tonicity and isotonic solutions.
Starting off with Section 1. Ionization and drug absorption.
Let's start with ionization. Basically, it's the process where a substance completely or partially dissociates into ions. And why does this matter? Because it dictates solubility, stability, and most importantly, absorption. When we look at electrolytes, there are two main players. Strong electrolytes, like sodium chloride, fully ionize in an aqueous solution. But what's super interesting is that most clinical drugs aren't like that. Most drugs are weak electrolytes, meaning they only partially ionize, and that really depends on their environment. We're talking about your everyday drugs here, like aspirin or penicillin.
And here is exactly why that matters. Think of the cell membrane as a bouncer at a very exclusive club. The unionized form of the drug is highly lipid-soluble, so it gets VIP access and crosses the lipid bilayer freely. On the flip side, the ionized form has really poor lipid solubility. It's totally blocked at the door and simply cannot cross over into the blood plasma.
So, quick recap. This is essentially the golden rule of absorption. Strong electrolytes are 100% ionized, weak electrolytes are partially ionized, and the unionized form is lipid-soluble and crosses those cell membranes best. This is the foundational building block for everything else we're going to talk about.
Moving right along to Section 2, pH, pKa, and equations.
First up is the classic pH scale, which measures how acidic or alkaline a solution is on a scale from 0 to 14 by tracking hydrogen ion concentration. In pharmacy, this simple little measure is literally everything. It dictates drug stability, it influences solubility, and it even controls whether a specific injection is going to burn a patient's tissues. Alongside pH, we have pKa. By definition, pKa is the negative logarithm of the acid dissociation constant. But in simple terms, it just indicates how strong an acid or a base really is. The quick rule of thumb to remember here is the lower the pKa, the stronger the acid. And this actually sets the stage for probably the most important mathematical relationship in pharmaceutics. Here is a pro tip, an absolute golden rule you need to lock in. When your pH exactly equals your pKa, the drug is exactly 50% ionized and 50% unionized. It's the perfect midpoint, and it acts as the anchor for predicting how any weak electrolyte will behave once it's inside the body.
To tie those values together, pH, pKa, and that ionization ratio, we use the Henderson-Hasselbalch equations. For weak acids, pH equals pKa plus the log of the salt concentration over the acid. For weak bases, it's the log of the base over the salt. This is the exact math pharmacists rely on to predict how a drug is going to ionize in, say, a highly acidic stomach versus neutral blood plasma.
Section 3. Buffer systems and capacity. Next, buffers. A buffer is basically a solution that completely resists sudden changes in pH when you add small amounts of acid or base to it. Our bodies actually rely on these physiological buffers every single second to survive. We have the phosphate buffer working between a pH of 6.8 and 7.4. We've got the bicarbonate buffer protecting our blood plasma. And in pharmaceutical formulations, we use things like citrate buffers to stabilize eye drops and oral liquids. So how does this protection actually work? Well, it's a team effort. You combine a weak acid, like acetic acid, with its salt, like sodium acetate. And the exact same concept applies to basic buffers too, like ammonium hydroxide paired with ammonium chloride. Introduce an acid, and the salt neutralizes it. Introduce a base, and the weak acid neutralizes it. It's this brilliant chemical balancing act that keeps the solution stable and prevents the active drug from degrading.
We actually measure the strength of this defense using buffer capacity, which is represented by the Greek letter beta. Buffer capacity is just a measure of how well that buffer resists a change in pH. Now remember our golden rule from a minute ago, that 50-50 midpoint? Buffer capacity actually reaches its maximum absolute peak effectiveness exactly when the pH equals the pKa. That's when the buffer is strongest and most efficient at preventing things like tissue irritation.
Section 4. Tonicity and isotonic solutions.
Finally, tonicity. An isotonic solution has the exact same osmotic pressure as normal body fluids, and the absolute gold standard reference for an isotonic solution is 0.9% sodium chloride. This number is non-negotiable. It's the target when creating anything like intravenous fluids with eye drops.
Because getting the tonicity wrong has some really severe visual consequences for our cells. If a solution is hypotonic, it causes the cell to drastically swell. If it's isotonic, the cell stays perfectly normal. And if a solution is hypertonic, it literally causes the cell to shrivel and shrink.
Let's methodically break these three states down. If a solution is hypotonic, meaning it's less than 0.9% NaCl, fluid rushes into the cell. The cell swells up and eventually bursts. This is a very dangerous condition called hemolysis, which spills hemoglobin everywhere. If it's isotonic, at exactly 0.9% NaCl, that normal cell shape is beautifully maintained. But if the solution is hypertonic, greater than 0.9% NaCl, water is actually sucked out of the cell. The cell shrinks, which is a process known as crenation. Maintaining that perfect isotonic sweet spot is absolutely critical for patient comfort and safety.
Bringing it all together, here is your master quick recall of today's highest yield takeaways. First, when pH equals pKa, your drug is exactly 50-50 ionized. Second, buffer capacity maxes out precisely at that exact same midpoint. Third, the unionized form of a drug is lipid-soluble and absorbs the best. And finally, 0.9% NaCl is the universal isotonic standard.
Which leaves us with one final thought. Remember, ionization is the key to absorption, and buffers are what keep our formulations stable. These aren't just equations you memorize for a test, they are the literal building blocks of bioavailability. With ionization, buffers, and tonicity mastered, how will you formulate the next life-saving drug? If you found this explainer helpful, make sure to subscribe to AllAboutRx for more high-yield pharmacy lectures.